Good morning, ma'am. My name is Shiva. I am from CSCF section in SRIT College. My topic name is about Gauss divergence theorem and example. Introduction to Gauss divergence theorem. The Gauss divergence theorem relates a vector field to fall of the field through a closed surface. It is fundamental theorem in a vector calculus and has applications in physics and engineering. The theorem provides a powerful tool for converting volume integrals into surface integrals. Understanding divergence. Divergence measures a rate at which expands from point in a vector field. A positive divergence indicates a source while a negative divergence indicates a sink. It quantifies how much a vector field I separates spreading out from a point in a space. Some conditions for the theorem. The theorem holds under certain conditions such as the vector field being continuously differentiable. The surface must be closed and oriented outward for the theorem to apply correctly. If these conditions are met, the theorem guarantees the equivalence of a surface and volume integrals. Example problem. Verify Gauss divergence theorem. F is equal to x cube minus yz into I bar minus 2x square yj bar plus z k bar taken over the surface of the cube bounded by a plane x equals to y equals to z equals to a and coordinate planes. Solution. Given f bar equal to x cube minus yz I bar minus 2x square yj bar plus z yk bar. By Gauss divergence theorem, integral as f bar into n bar cap into ds equals to integral v del f bar into dv. This is considered as equation 1. Then del f bar equals to dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou d. Then dou by dou x of x cube minus yz plus dou by dou y of minus 2x square y plus dou by dou z of z. After differentiation, 3x square minus 2x square plus 1 del f bar equal to x square plus 1. Now RHS integral v del f bar into dv equals to integral 0 to a integral 0 to a integral 0 to a x square plus 1 dx dy dz equals to integral 0 to a 0 to a x square z plus z over the limits 0 to a dx dy. Another time we can substitute the limits a x square plus a into dx dy. Then common a integral 0 to a integral 0 to a x square plus 1 dx dy. After integration x square y plus y integral 0 to a into dx. After integration a square into x cube by cube 3 plus x over the limits 0 to a. Then RHS a power 5 by 3 plus a cube. Then calculate LHS. Here the surface is a cube bounded by the x is equal to 0 to x is equal to a and y is equal to 0 to y is equal to a and z is equal to 0 to z is equal to a. The cube consists of 6 faces. Then integral s f bar n bar cap into ds is equal to surface integral s1 f bar bar n bar bar ds plus up to integral s6 f bar n bar cap into ds. This is considered as equation 2. For surface s1 pqas integral s f bar n bar cap ds equal to integral y is equal to 0 to a integral z is equal to 0 to a x cube minus yz I bar minus 2x square by j bar plus z k bar into I bar dy dx. Put x is equal to a. Then integral y is equal to 0 to a, z is equal to 0 to a cube minus yz dy dz. After integration and substituting the limits, the surface S1 equals to a power 5 minus a power 4 by 4. For surface S2, OCRB, integral S f bar into n bar cap ds equals to y is equal to 0 to a integral z is equal to 0 to a x cube minus yz I bar minus 2x square by j bar plus z k bar into minus I bar dx dy. Put x is equal to 0, integral y is equal to 0 to a, z is equal to 0 to a, yz dy dz. After integration and substituting the limits, surface S2 is a power 4 by 4. For S3 surface, R 0 to a into x cube minus yz into I bar minus 2x square yz j bar plus z k bar into dx dy. Put z is equal to a. After integration and applying limits for S3 surface equals to a cube. For S4, OASC integral S f bar cap into n bar cap ds equals to integral x is equal to 0 to a, y is equal to 0 to a into x cube minus yz I bar minus 2x square yj bar plus z into k bar into minus k bar dx dy. Put z is equal to 0, then integral x is equal to 0 to a, y is equal integral y is equal to 0 to a minus z into dx dy. For S4 surface equals to 0. For S5 surface, PSCR integral S f bar n bar cap ds equals to integral x is equal to 0 to a, integral z is equal to 0 to a, x cube minus yz I bar minus 2x square by j bar plus z k bar into j bar dx dy dz. Put y is equal to a. Then integral x is equal to 0 to a, integral z is equal to 0 to a minus 2x square a into dx dz minus 2a integral 0 to a x square into z up to limits 0 to a dx. After substituting limits for S5 surface minus 2 a power 5 by 3. For S6 surface, integral S f bar into n bar cap into ds is equal to integral x is equal to 0 to a, integral z is equal to 0 to a, x cube minus yz I bar minus 2x square by j bar plus z k bar into minus j bar dx dz. Put y is equal to 0. Then S6 surface is equal to 0. From equation to integral Sf bar into n bar cap into ds is equal to a power 5 minus a power 4 by 4 plus a power 4 by 4 plus a cube plus 0 minus 2 a power 5 by 3 plus 0. A power 4 by 4 minus a power 4 by 4 cancel, then LCM of a power 5 and 2a power 5 by 3, then a power 5 by 3 plus a cube. LHS equal to RHS, hence divergence theorem is verified. Conclusion: the Gauss divergence theorem is a cornerstone of a vector calculus with wide-ranging applications. Thank you, ma'am.